Right, good evening and welcome back to session 1.4, I think. And what we're going to do this evening is, in a sense, continue from where we left off last week. Last week we didn't actually talk too much about the idea of Brownian motion. I know when we looked at the observation section, it did say in one of the bullet points that this is Brownian motion. But that was as far as we got in terms of talking about that. What we're going to be doing this evening is looking at how to extend the normal rules of everyday calculus to look at calculus in a stochastic world. In other words, if you've now got functions of a random variable, what are the new rules of calculus? Because the old rules aren't going to work. So the reason why this is called stochastic calculus and Ito's lemma is because we're going to be looking at this new idea of calculus and also looking what happens to Taylor series when the function becomes a function of an underlying variable which is a time-dependent random variable. So we'll talk about the idea of what it means to be a stochastic process or a stochastic variable. So what we're going to be doing this evening, in this evening's lecture, is first of all we will look at construction of a Brownian motion. Notice we say a Brownian motion. We don't say Brownian motion because Brownian motion isn't a particular thing. It's essentially a type of distribution. And we'll talk about that in detail this evening. So construction of a Brownian motion. Then we'll look at properties of a Brownian motion. Ito's lemma. And then an introduction to stochastic differential equations. It'll be fairly informal because Thursday is going to be used to look at stochastic differential equations in a lot more detail. So that's the course of action for this evening. And the idea is that by the end of the 2.5-hour session, you will appreciate Brownian motion and diffusion processes. You'll also be happy about what it means to be a stochastic process. A stochastic process. And also how to manipulate functions of random variables. So our random variables are now in fact going to be stochastic processes. What we're interested in looking at is random variables whose outcome depends on time. That's the idea behind this evening. Right, Good Evening says, last time there was a mention of a book containing all formulae from calculus and statistics. I guess I did not get that. Also, what's the title, author of the book? I don't remember. Did I?
Talking about the notes that you said last week.
What's that?
I think you said you would get some notes, so detailed working instead.
Oh, but those went out.
Yeah, I think you mentioned that.
Well, maybe. Well, Michael Patterson says numerical analysis by Burden and Fairs. That's not the same as calculus and stats. So, if that answers the question, then good. But I doubt whether I would have said that there's an amazing book out there on calculus and statistics. Right, everyone happy with what we've got planned for this evening? So what does Paul? So again, for these notes, there's going to be a lot more stuff to follow. Right, these are not my slides. So the reason being that I make very poor slides. My slides are absolutely awful. I'm better at writing A4 style notes, but certainly not slides. So it makes more sense to use Paul's slides and then fill in all the missing working, and then also give you some extra notes. There's only so much you can have on the slides anyway. So what does it say? It says stochastic calculus is very important in mathematical finance. I think we all appreciate that. This is because the underlying random nature of financial markets. In other words, whether you talk about a stock, an interest rate, a commodity, an index, they are all examples of stochastic processes. And that's the reason why we need to get a good understanding of stochastic calculus. In other words, how do we do differentiation and integration when we now have functions of stochastic variables? So this is a very nice motivating example, as Paul says. There are many ways to construct a Brownian motion. Some are very, very theoretical, some are very applied. With this is a combination of both. So what we have here that Paul's done is a very nice way of deriving a model for Brownian motion. And a lot of probability, a lot more than you think, is based on the idea of this coin, this fair coin. So everything that we talk about this evening is going to be based on tossing a fair coin and then following what happens. But before we do that, we need to define what the rules of this game are. So this is going to be based on a gambling game, where we toss a coin. It's a fair coin. Each time we get a head, we get a pound. Each time we get a tail, we have to give a pound away. So that immediately tells us that that sounds very much like a random variable. Remember, we all know that a random variable is simply some kind of rule or mapping which assigns to all outcomes of a sample space a real number. In this case, the mapping, or the rule, simply says that the probability of a head is +1, the probability of a tail is -1. So that's our rule there. So let's write this down. And you can see quite clearly that what happens. Let's just have a quick look at what letter is used. Right, so the first thing we say is that Ri, this random variable Ri, is equal to +1 if it's a head and -1 if it's a tail, because then we get to write down that the probability of +1 is a half, as is the probability of -1. So there's our random variable, Ri, +1 if it's a head, -1 if it's a tail. And in this particular case, you see that after 1, 2, 3, 4, 5, 6 tosses of the coin, we've actually broken even. Important rule of the game also is that at the start of the game, you start off with 0 innings. And the idea is after a large number of tosses, you see exactly where this random walker has taken us. That's the idea behind this game. Right, so it's either +1 or -1. So the obvious thing to ask yourselves then is that if that's the random variable, let's examine the statistical properties of that. And that usually means let's look at the expected value. So the expected value of this, Ri, remember, go back to basics. Right, let's make this a bit more readable. Expected value of Ri, remember, you simply multiply the probability with, each outcome by its probability. So +1 times a half, plus -1 times a half. So that gives us 0. So the expected value of Ri is 0. The variance of Ri is simply +1 squared times its probability plus -1 squared times its probability. So that's 1. Those are the properties of that particular random variable. So that's simply telling us that on average that we would expect to have 0. On average. Remember, we know that each time we toss the coin, it's either going to increase by 1 or it's going to decrease by 1. It certainly can't stay the same. But this is telling us on average. And this is the idea behind a basic fair game. Because we started out with nothing, we should expect to, in the long run, have nothing. it's also a fair coin. If you're wondering what would happen if it was an unfair coin, then the results would be something very, very different. And that wouldn't lead us to Brownian motion. The idea for us is to get something which models a Brownian motion. So this is exactly what we have. The other thing right at the end that's given comes from the fact that subsequent coin tosses are independent. So hence we've also got that. Because remember, this allows us to write that the expected value of Ri times the expected value of Rj, expected value of Rj is equal to 0. That's how we get that. That's important. Now what does Paul say next? In this example, it doesn't matter whether or not these expectations are conditional on the past. All right, we'll come on to the idea of conditional in a second. Now, the only problem with this game is that you may want to know after the ith toss how much you've got. At the moment, Ri doesn't do that. It simply will tell us that on the 100th toss whether we've won a pound or lost a pound. So the next thing to do is introduce a new random variable which keeps a score of our winnings. And this is now Si. So Si is equal to the sum of Rj from j equals 1 to I. In other words, it's what we have in our hand after the ith toss. Right? Are you happy with that? Subject to the very important condition that at the beginning, subject to S0 equaling 0. That's a basic property. So we are fixing that because there's going to be no uncertainty as far as that's concerned. Right, everyone happy with that? What did he say then? Later on it will be useful to have, yes, right? So that's what we've got so far. And as before, let's look at the statistical properties now of Si, which is exactly what Paul's done here. So let's examine that. First of all, expected value of Si, all we need to do is really do the following. Let's do this here. Expected value of Si is simply expected value of this thing here, Rj, where j goes from 1 up to I. And this, we can take the expectation operator inside. Why? Because of the linearity here. So we've got the sum of the expected value of Rj. J goes from 1 to I. And then we've got I lots of 0, so we get 0. So that's the expected value of Si. What about the variance? So Si is equal to variance of this thing here. J goes from 1 to I, and let's take that. Remember, the variance is also an expectation. It's a higher order expectation. But if we do this, what did we say the variance of Rj was? It was 1. So we got I lots of 1. So this equals 1. Sorry, equals I. If you want, let's also have a quick look at how Paul's done it. I.e., you simply expand everything out, which is what Paul's done. So let's have a quick look at that also. The reason being that later on, when we get towards the end of all of our derivation, it'll help. So let's do that. Let's just quickly go back here and have a look at this. Now, what Paul's done over here is he simply said that the variance is equal to the second moment minus the square root of the mean. But the mean is 0. So all we need to do is we need to examine this. So that's another way of writing down the variance. Remember, the variance equals the second moment if the mean is 0. They're both the same thing. All right, is everyone happy with that? So all we do is we simply look at the sum of Rj and open it all out. And this is what we end up with. And what's going to happen is you're going to have all of these square terms coming in, but then also the cross-term products there. Right? And because of the independence of subsequent coin tosses, or the independence of them, these terms, all of these terms will give us 0 when we take the expectation operator inside. But then we're going to have expectation of r1 squared plus r2 squared all the way up to ri squared. Agreed? So there's a whole load of 1s, I lots of them. So that's why we get I. So when we square this, all of these terms vanish. All we're left with is the sum of the rj terms. Right? So you end up with the same result. Whether you do the quick thing like I just did, or you open all of this out, and then you examine every single term. Okay? Now, the next point is important. It says that suppose there have been 5 tosses already. Can we use this information, and what can we say about expectations for the 6th toss? Now, remember, conditional expectations is all about having previous information. So if you have prior information, it's supposed to assist us with work calculating probabilities and expected values for forecasting what the future is. So suppose you wanted to say, what's the expected value of S6? Right? In other words, our winnings on the 6th toss, given we know what's already happened here. Right? Now, in going from S5 to S6, what do we know the expected value is? It's either going to be a half times plus 1 plus a half times minus 1. So on average, it's going to be 0. And that's the reason why we can say that the expected value of S6 given S5 is in fact the money we have already, on average. Obviously, remember, you're doing this many, many times. And that's the idea of a conditional expectation. And that's going to be very, very important for us in finance. Okay? We know that if we're at S5, it can't really be still the same at S6 because we're either going to go up by 1 or going down by 1. But we're not talking about that. We're talking on average. We're talking about expectations. There's another property that's very, very important here, and that's the Markov property. That's another type of expectation, a conditional expectation. What this is actually saying is, that the expected value of S6 given S5 is just simply what we already have. The Markov property is something different. Let's read this and then we'll go through it. It says the distribution of the value of the random variable Si conditional upon all the past events only depends on the previous value Si minus 1. Suppose you want to get a conditional expectation or some kind of idea of what the distribution is going to be at Si given Si minus 1, this property is simply saying that everything prior to Si minus 1 has been forgotten. How it got there, it has no idea. The only information that's useful for us to try and figure out where we might be in the future is the information contained at this particular point. Now, contrast this to the coin tossing experiment. Suppose at S10, we know where S10 is. We want to use S10 to try and work out some kind of distribution for S11. How we got to S10 isn't really important. What's important is that we know what the value of S10 is. Because to get to S10, it could have gone using a series of up-down movements or down-up movements. That's not important. We're assuming that it's forgotten how it arrived there. But the only information that we need in order to work out what the future distribution might be is what's contained here. So in other words, our winnings at that particular point. That's the Markov property. You can see sometimes it can be confusing to try and distinguish how this is different to the previous one. Now, how does this differ from that? Because not all processes are Markov, not all processes are, well, I don't want to use that word just yet. Right, so when you look at this, how does this differ to that? The Markov property is saying nothing about where it might be in the future. All it's saying is that the information contained at I minus 1 is the only information required for us to try and work out expectations for the future. In the previous case, it's actually saying that on average, we would expect it to be the same. So it's actually giving us a value on average. Markov is not saying that. Markov is simply saying that how it got to this particular point is all that's important. It's forgotten how it got there. Once you look at that particular point here, that's Markov. And that's the reason why the Markov property is sometimes called a, the word is here, given here, it's called a memoryless state. In other words, a process that has no memory. That's Markov. So the one that we just looked at was the Martingale property. The conditional expectation before, this is called the Martingale property, and next Tuesday session is going to be all about the Martingale property. Right, so let's have a look at this. It says here that the coin tossing experiment possesses another property that can be important in finance, and it's actually the cornerstone of finance when it comes to pricing derivatives. It's going to be very, very important. So here we go. It says that the conditional expectation of your winnings at any time in the future is just the amount you already hold. In other words, you're looking at a conditional expectation at point J to try and figure out where you might be at point I. So all this is simply saying is, say, this is S6 given R1, 2, 3, 4, 5, which in other words is S6, S5. So the expected value of Si given Sj, where Sj is less than I, and this is taken at time or point J, is simply equal to what you already have. So the information you hold at this point is the best forecast for the future. That's what the Martingale property is saying. So two different properties that this game possesses. Okay? Markov and Martingale. And this is something that's going to come up over and over again.
Is the Martingale property a special case of Markov property?
No, they're not the same.
No, is that a special case of Markov property? Because we're saying that here the expectation of SI is in the previous case.
No, I know why you're asking that, but the answer is still no. They're two distinct properties. So we can't say. So the question that's being asked for the distance folks is that is Martingale a special case? You can think of it as, but it isn't, if that helps. I'd be wrong to say that it is. And I know the reason why you're asking that is because whilst the Markov seems a lot more vaguer, it seems a lot more general, this is specific in saying that this says nothing about the fact that it's forgotten everything, which is what the Markov is saying. Right, was your hand about to go up?
Yeah, so is Martingale property same as saying that the mean of your random variable is 0?
In this particular case, it would be. But so again, distance folks, our friend is asking, is it the same as saying that the mean is 0? In this case, yes. Generally, what we would say that it's a constant mean process. So the fact that in this case, the mean is 0, it's not changing. So you're absolutely right in asking that question, and the answer is yes. But generally, there are many, many different types of processes, not just Brownian motion, for example, and there the mean wouldn't be 0. As long as it doesn't change, it's a Martingale. So are you happy with that? Because the question you asked was, is the Martingale property saying that the mean is 0, right?
Yes. So in this case, if the mean was k, let's say, then what would be the expectation of Si given Sj?
If the mean was k, you mean some fixed value? Yeah, it wouldn't change. It would remain k.
Wouldn't be Sj plus?
No, you're asking what the value would be. That's what you're asking. So the idea that it's a constant mean process means it would always be k, right? Where in this case, k is 0.
Now, another important property. When it comes to stochastic processes or any type of movement, random walk, what we're interested in often is looking at how the movement varies with time. In other words, let me just draw you a quick sketch here. Let's draw this here. Suppose you've got something like this. What we might be interested in, over a given time, how does that rise? Is it fixed? Does it grow indefinitely? And what allows us to measure those changes is a variation. Within variation, there's a special type of measurement called a quadratic variation. And the quadratic variation is simply the sum of the squared changes. So have a look at this. So let me just write this down as Q. Q is equal to this, right? Quadratic variation. So for this coin tossing experiment, where we're looking at S, in other words, our winnings, is simply the sum of the squared changes. Can you see, from going from one toss to the next? Which means that this value is always going to be plus minus 1. Agreed? The way that's normally written in books is usually with an absolute sign like this. Let me just, these are growing. How is this different from Markov? Now, is Markov the superset of martingale? No, I think we've answered those. Can the Markov be the starting point for the martingale? Not really, because stochastic processes is a subject in itself. So you can study stochastic processes and all about Markov processes of stochastic processes without ever touching martingales. Martingales have become particularly popular because of finance. Although martingales have been around for a long, long time, a lot of these things are simply popular because of quant finance, so no other reason really. They've been part of probability theory for decades and decades. But because they started getting used for pricing derivatives, all of a sudden the popularity went up. Right. I think the point of Markov is that the stochastic space is memoryless, but the main point of Markov is the future expectation for stochastic process is equal to the current value. Right. So yeah, Ramtin, you put that, or should I say, summarize that very well. i.e. the difference, where one talks about, I mean, they are still expectations, both are, but one simply says that the future value is going to be essentially the information that we already have. Now, have a look at this. So, the quadratic variation is given by this, and because we either win or lose an amount of £1 or $1 after each toss, it means that this value is going to be 1. So if you have I lots of them, we see that the quadratic variation is I, which happens to be the same as what the variance was. That's purely coincidental. You do not normally have that the quadratic variation of something is the same as the variance. But in this coin tossing experiment, because it's very, very important and it's designed in such a way, we find that the quadratic variation is I. Now, what will happen if we do an infinite number of tosses? What do you think? If we toss this coin an infinite number of times, what will happen to the variance and the quadratic variation? It'll grow indefinitely, which we don't want. We want the same as last week. Last week, we were interested in a random walk which remained finite, in finite time. We didn't want a random walk which either collapsed to 0 or blew up. It's the same over here. Right? So far, we haven't said anything about time. Right? Brownian motion, which is what we're trying to construct, is a time-dependent random variable. In other words, a stochastic process. So at this point, we need to introduce some concept of time into our game. Because at the moment, we're just tossing this coin, and we haven't said anything about the time in which we play this game. The other thing is, clearly we can see that a game with a bet size of £1 or $1 isn't a good idea because of this. If we do this an infinite number of times, then this is going to blow up. So let's introduce the idea of a timed game.